Okay, my name is Charles Payton. I'm an physics major. This is my second bi-weekly progress report for REU. Dr. Claudio Mantelli is my mentor, and I'm working with graduate student John Chata. Last week, my presentation was on thin film thermocouple design implementation. This week, I'm going to give my presentation on the fabrication process. Last week, if you remember, part of my design and implementation, we had to get our thermocouple readings to go from testing into the actual fabrication. This is a chart of the voltages that our thermocouple was giving. These are the voltages we were getting according to our temperatures. This is a simple chart of those voltages and temperature. As you can see, it's pretty much linear. The basic term of the fabrication of thin film is termed physical vapor disposition. And basically all we were doing is taking whatever elements, whether we're using silicon dioxide, or whether we're using germanium, or whether we're using, in our case, we're going to be using copper nickel. But all we're doing is heating it up into a form where it vaporizes to a substrate. There are three basic types of vaporization, physical vaporization. There's resistant heating, there's sputtering, and there's electron beam. Resistant heating basically takes an element and heats the material to a temperature to vaporize. Sputtering takes and uses an inert gas like argon, and it heats that gas until it turns into a plasma, and that plasma, along with ionization, takes our source material and vaporizes it. And because it is ionized, it is attracted to our substrate. And the one we're going to focus on the electron beam vaporization. And what this does, it takes a high energy electron beam controlled by a magnetic field, and it focuses our source material with a electron beam until it vaporizes and the vapors are attracted to our substrate. This is a picture of the machine that we were using. If you remember, in my last report, we said we would be using the magnetron sputtering system. Well, we changed and decided to use the IBAD. IBAD stands for Ion Beam Assisted Electron Beam Deposition System. This is a simplistic cartoon, I guess you will, of how the IBAD works. What you have here, you have 3 electron guns, and either one of them or all 3 of them, we can put our source material, whether we're using semiconductor material like silicon or germanium, or whether we're using a metallic material like copper or silver. These are where this will go. And what happens is our guns put out an electron beam that are steered by the magnetic field, and it heats up and vaporizes our material. And as it vaporizes, the material becomes the atmosphere, is attracted to our substrate. And the ion gun, what that does, depending on the material you will be using, depending on the density of the material, the ion gun produces ionization that enhances the attraction of our vaporized molecular material to our substrate to give us our thin film production. There are a part of our IBAD. I'm going to go into a part of our IBAD components. Our IBAD, the beginning portion of our IBAD components are our guns. There are 2 types of guns. We have 2 low power electron guns, and we have 1 high power electron gun, and we have 1 ion gun. This is a simplistic view. Before I show you a picture of our guns, this is a simplistic view of exactly how our electron gun works. We have our guns, and the IBAD itself is made. The IBAD is made of stainless steel. Our gun is made of oxygen-free, non-conductive copper. I believe I'm saying that right. But we have a crucible here made of carbon. We have a filament that produces electron flow. Our magnetic field is what guides our electron flow, and our electron flow is steered into our source material and then vaporized. This is a picture of us actually opening up the IBAD. This is the system where our guns are. I should have a picture right there. Okay. After you open up this machine, if you look on the inside, this is an ion gun. They have it covered up because they don't use it every incident when they're vaporizing material. So when they don't use it, cover aluminum foil, because once these materials are vaporized, these vapors go everywhere. So they don't want to go on the gun if the gun's not going to get used. But here is our low power electron gun. Here is another area here where it's supposed to be another one, and that's what they're in the process now of putting this gun back together. This is our high power electron gun. And like I said, which gun we use depends on what type of material and what type of vaporization we're trying to achieve. Now, the way this process works with the electron guns and vaporizing materials, as you know, things like oxidization and things of that nature, these things can't happen in a normal atmosphere. So the IBAD has to be vacuumed down to like so many torr, and this one has, different types of vacuums. There's rough vacuum, there's high vacuum, and then there's ultra high vacuum. There are different types of vacuum pumps. This is a regular vacuum pump here. This is what they call the high vacuum pump, which uses cryogenics. And if everybody is familiar with cryogenics, we use cryogenics because that takes it down to an even farther level of vacuum. All right, and the reason for our vacuum is because we want a mean-free path of molecules. Mean-free path, I'll get into that in a minute. But we want to prevent chemical reactions like such as oxidization. We want to reduce particle flux, and we want to allow the operation of our sensitive components like the high voltages, a lot of the thermocouples and things of that nature. A lot of the sensitive sensing equipment that we have inside the IBAD are function inside of the vacuum, low vacuum atmosphere. Now, as far as the mean-free path, that terminalizes because, as you know, in regular atmosphere we have air of composition of all types of different elements and molecules of different elements. So if we vaporize a material and we have a substrate that we want our vapors to adhere to, then we've got to vacuum our atmosphere down so that when the atoms of our source material start to vaporize and start to expand, we want to ensure that they are attracted to our substrate. So depending on the materials we're using, and depending on the materials we're using, depending on what type of substance that we're trying to develop, that's what determines how much vacuum we want. And this is basically a chart that is saying that, okay, on average, pressure fractions of atom, this is atmosphere. These two lines show our rough vacuum. This line shows our high vacuum. This line shows our ultra high vacuum. Now, the torr is the amount of pressure of vacuum that we're applying to our system. The number of density shows that how many free particles of air are actually in the atmosphere at the time of vacuum or atmospheric pressure. The mean free path, which is the main one we're concerned with, means that after our material vaporizes and the particles actually start to expand, how far will our particles of our source spread before they actually collide to prevent collision? Because we want our particles to expand and hit our substrate instead of bumping into something and just laying around inside our atmosphere. So Basically, all this is saying is, okay, once I vaporize this, how far will it spread? This indicates how much material will vaporize and actually go to our substrate. This is showing you the vacuum range of pump ranges of our different pumps. Your mechanical pumps will pump anywhere from 0.01 to 760 torr. I think they got this backwards, but our cryo pumps will. Oh no, that's right. Our cryo pumps will go down to approximately 10 to 8 to 10 to 4 torr, and our ion pumps will go even farther down there. Now, ion pumps, I'm not real familiar. Like I said, I just started getting into this area of our technology, but basically, torr is saying how much vacuum we have on our system. There's at the end of the day, the main thing we're trying to do is produce our thin film couple. There are only certain variables that we can control. We can control the temperature, we can control the distance of our substrate, and we control our electron flow to our source. And they internalize this as our PVD recipe. My next presentation, I will be starting to get into more of what happens to our substrate. There are some things, when I say our substrate, there's some material that we're actually going to be flowing our vapor to. Outside of the distance, we can rotate it so that if you know at any vapor, if you have something rotating or moving, it's more likely to pick up the particles. But I'll get into more of that in our next presentation.